Thank you for joining me in this interview today. To reiterate, my name is Annie, and I create Sustainability Beyond the Lab to make sustainable research more accessible for general audiences, as well as showcase the barriers that prevent their scale up. To start, could you also introduce yourself and tell us about your research, especially at MIT?
Yeah, absolutely. So, hi everyone, and thank you, Annie, for the invitation. My name is Marcos Farpón, and I am originally from Spain, where I spent some part of my previous training. I was around Europe, and then I came back to Valencia to do my PhD in the context of the design of novel catalysts in the context of gas phase conversions of various sustainable hydrocarbons. And then I moved to MIT. Actually, my first time in MIT was not for my postdoc, but rather for my research stay doing my PhD. I spent 3 months during the summer of 2023, where I started working on the conversion of pretty much plastics recycling and biomass upcycling. And that was the thing that next would move towards my next research stage, which is now as a postdoc, where I started in fall 2024. And my main research lines here are in the context of designing novel catalytic processes for processing complex carbon feedstocks, mostly biomass, particularly the lignin fraction of biomass. But I've been also involved in the upcycling of different plastic wastes, such as, for instance, polyethylene, polypropylene, or others. So yeah, that's in general terms what we do in the everyday.
Thank you for that overview. I've noticed your research focuses on, as you mentioned, converting biomass and plastic waste into more valuable fuels and chemicals. For people who
Mhm.
aren't familiar with like the technical aspect of this field, what problems is this trying to solve, and why is this important for like the for sustainability?
Yeah, absolutely. So nowadays, most of the either fuels or products are based on different industrial processes for which the traditional industry is based on at the end carbon feedstocks. Carbon is one of the main elements of life, and we use them in multiple conversion processes to make these fuels and chemicals. And most of the carbon has traditionally come from non-renewable resources, so for instance coal or petroleum, oil, or natural gas. Now the thing is, we are trying to design new processes that move towards other types of feedstocks, which at the end they are in essence carbon, but the carbon is from another type of origin, and this has different advantages, such as, for instance, in the case of biomass, which is a term that refers to different types of carbon feedstocks from different origins. It can be good from forestry residues. It can come from food residues or different types of crops. At the end, they contain carbon, but it's carbon in, let's say, in another fashions or in another different types of structures. So the idea is trying to exploit chemistry, engineering, and particularly the field in which I am working, which is catalysis, to try to adapt using different feedstocks these processes to extract molecules that can be used either for chemicals or for fuels with similar applications and without trying to change too much the infrastructure we have nowadays. Similarly, from biomass, it happens in a similar way to plastics. There is a lot of waste produced from plastics, and the idea is instead of having an open loop economy, why don't we try to make circular systems that
Mhm.
allow to give value via multiple cycles and closing the carbon loops in the plastic scheme.
Yeah. Um, That's really interesting to hear how like these plastics and biomass can be essentially like, or specifically the plastics can be recycled and made into newer materials that can be reused. I've noticed one of your projects involving converting lignin into sustainable aviation fuel. Um,
Mhm.
since lignin is often considered a difficult material to utilize, what makes it such a promising feedstock?
Yeah, that's a great question. Actually, this connects kind of like what I was explaining before on how at the end we are talking about processing mostly carbon, right? Which is one
Mhm.
of the major elements in most of these different processes and actually in nature and in life. And the thing is that just to give a rough and a general sense, lignin is a very promising feedstock because it's one of the major sources of aromatic molecules in nature. So, long story short, aromatic molecules is just one type of hydrocarbons that they have specific structure, particularly um, rings of forming like hexagons of 6 carbon atoms with some double bonds. And these are interesting because they have a wide use of applications for making chemicals on different platforms in the chemical industry, but also they are very important for fuels and particularly for aviation or jet fuels. The reason for this is because fuels are normally comprised by molecules of carbon and hydrogen, so hydrocarbons, of different sizes in terms of chain lengths of carbon. And particularly for aviation, it's between 8 and 16 carbon atoms. But the interesting thing is that it's not only about the length, but also that we need to have different configurations. And one of these configurations is the aromatics, which provide specific properties for the fuel, such as, for instance, making sure that that some of the connections in the genes or the oil rings don't leak and make the adequate swelling. So that's why lignin is so interesting because it has a beautiful structure comprised mostly of these aromatics. But in the current processes employing biomass at the largest scale, which is primarily the pulp industry for paper manufacturing, this industry is interested in extracting the cellulose for making paper, but the lignin it's kind of like a residue, and it's very difficult to valorize because of the conditions at which it's exposed, therefore making difficult the upcycling. And that's kind of where we start working on, trying to extract the lignin, preserving the original structure, or let's say the closest to the structure in nature, and trying to make an upcycling process to exploit the nice value of its native form.
Mhm. Yeah, I see now why lignin is such a good feedstock for these like fuels.
Oh, yeah.
Focusing more on like plastic recycling side, how does your approach compare to like other processes for recycling or um, like without recycling, just like this one way process?
Yeah, well, I have to say that like the problem of plastics also with biomass, this kind of carbon feedstocks, as I was mentioning before, is that if you remember, I was mentioning that they are complex carbon feedstocks, and the reason for this is because that in industry, most of the processes are based on starting with feedstocks that are either gases or liquids,
Mhm.
or of course there are processes based on solids, but one of the challenges in the context of plastics and biomass is how heterogeneous these feedstocks are. So imagine in plastics, we might be working on trying to make recycling processes for polyethylene for polypropylene. But then the reality is that we have a mixed plastic waste stream that it's uh, containing a whole bunch of different plastics, other kinds of impurities, and that's one of the biggest challenges of that. That being said, that's why most of the plastics based processes for recycling uh, have struggled with some of these impurities or these different mixing between plastic waste. So a whole bunch of the plastic nowadays is either landfilled or incinerated. And most of the plastic recycling strategies going on are based on mechanical recycling.
Mhm.
But there is interest, of course, in designing chemical recycling, which in an ideal scenario would allow to break the polymers back into the original constituents or monomers. That's why they are called polymers, because they are formed by multiple units of these monomers. And that would be kind of the ideal scenario, but in many cases, this is not possible, and we'd rather try to give it a second life or a second chance for high-value chemicals or fuels. Yeah.
Um, I've also noticed your work emphasizes like continuous catalytic processes. Why are these continuous systems so important for like scaling these technologies?
Mhm. Yeah, so in industry, particularly when we're talking about in the chemical industry,
Mhm.
um, one of the first things we learn when we are chemical engineers or when we are studying undergrad is exactly this type of different processes, how you have a batch process versus a flow or a continuous system. And you can think of a flow of a batch process like similarly what would you do with the kitchen, right? So you make a pot, you put your stuff in there, you cook it, you close it, and after a certain time you open and you have your meal, right? Your food. Um, in the case of the chemical industry, would be the same, but instead of with food, just putting your raw materials, converting them. But then this has different problems associated and limitations in terms of productivity because it's require operating in cycles and so on. Whereas in a flow process, this is very interesting because ideally we would operate in the so-called pseudo steady state or steady state. You are producing things in the regardless of time, and you are having a continuous supply of product. And not only that, but also this allows to change conditions if things are changing with time, so you can control your process and have different control metrics. But of course, that's kind of like the dream scenario and can be done in many cases. But for some feedstocks complex, such as, for instance, plastics or biomass, this has different limitations.
Yeah.
You would think of a process using liquid or gas raw materials or feedstocks. You can pump it or you can flow it through a reactor or through a process unit, and it's relatively easy to do. The problem is that when you have solids or when you have a plastic melt that is super viscous or biomass stream comprised by solids, things start to become more complicated and there are many technical limitations described. So that's one of the challenges, but pretty excited to be working on that.
Yeah. What do you see as the kind of biggest barriers that prevent, for example, plastic recycling or converting biomass from becoming adopted on like a very large scale? And would you say those barriers are like primarily economic, based on the scientific innovation itself, policy driven, or just like a kind of combination of all of these?
Oh, yeah, no, that's an absolutely very good point. Because at the end, when we're working in the lab, we
Mhm.
sometimes design technologies based on some metrics, on some descriptors, such as, for instance, how efficient is my process? So, say, for instance, I am starting from raw material or reagent A, and I want to convert it into B, right?
Mhm.
And I want that reaction to proceed at the highest yield possible. So, I want to
Yeah.
convert my 100% A into 100% B. That's kind of like the ideal scenario, right? But then, of course, there like real life is much more complex, and you start having other side products, PC, and so on. So imagine even when you do a perfect process at the lab scale, one of the biggest challenges is the scale up. How do I go from processing 50 grams of biomass or 5 grams of biomass or plastic waste into the kilogram scale and then into the ton scale ultimately? And while you're scaling up, 99% of the times there are problems. Say if you're working with a process unit, a reactor, what we call, right, the recipient where we make a reaction, you can control very well the temperature, the pressure, the steering, everything. But then imagine going to a pod that it's like in the cubic meter scale.
Yeah.
Things become more tricky. So scaling up is always a problem. Then the cost of the feedstocks sometimes can be really problematic. And then, of course, the consumption of the site, not reagents, but let's say elements required. Normally, these processes require solvents. If you need to use a lot of solvent, that's going to be very demanding in terms of the techno-economic analysis. Similarly, for hydrogen, this process require in many cases hydrogen. So having access to hydrogen that can be cheap, that's of course another of the metrics. And there is another whole bunch of things associated and it's process specific, but these could be some of the
Yeah.
examples that
Yeah.
I think would illustrate that well.
Yeah. Thank you for sharing those like specific examples. Looking
Mhm.
ahead, maybe 10 to 20 years, what developments in like sustainable fuels, or chemical recycling are you very excited about?
Mhm. Well, I think like the chemical industry has been there for a while, like over the last century particularly, and there has been a big evolution, and particularly with trying to design new processes. One of the challenges, as I was commenting, is trying to get the processes we have and how we adapt them from feedstocks that have been traditionally used into the new set of feedstocks, right? And at the end, there is kind of like let's say, a coexisting changing trend, right? Because we cannot shift from what is existing to the whole new set of processes, but rather smooth transition, right? And coexisting different types of technologies. That being said, I think it's very exciting that we have been traditionally based on working with oil and gas and coal, but there are processes that have been able to adapt towards these new types of feedstocks and do this kind of co-processing things. On top of that, I also really like, as an example, how we can exploit the knowledge of those other processes to adapt to these new feedstocks. For instance, in the context of these sustainable aviation fuels, we are working doing synthetic jet fuels. How can we take different feedstocks, produce ideally the same type of molecules, and repipe it towards this
Mhm.
new type of directions. I think that's something pretty exciting and similar for plastics, right? Traditionally, there has been a lot of mechanical recycling, but we are also working a lot in this chemical recycling space. So hopefully, finding catalysts that can tolerate these impurities, these is complex feedstocks. I think it's something pretty exciting, and hopefully will have a positive
Mhm.
impact in the near future.
Before we wrap up, is there anything that we didn't get a chance to discuss during the interview that you think is like important for people to know about sustainability in general?
Well, I mean, I think maybe like a general comment and something which is probably one of the things that I enjoy the most in my work. And of course, I'm happy to take any other questions.
Mhm.
But I think something that it's very cool about working on all this is that it's really a multidisciplinary problem. It's not about being a chemical engineer or being a industrial engineer or a chemist or a physicist or a physics. It's more about like how can you combine different expertises and to solve problems. And that I think that's really one of the drivers and the cool things in research, right? Because when I started my postdoc, I had experience like in the more conventional catalysis background, right? But
Mhm.
in these plastics and biomass chemistries, there is a lot of organic chemistry, a lot of polymer chemistry, and many other different things. We work a lot also with environmentalists. We work also a lot with the techno-economic team assessment, right? And I think that's one of the big things. So long story short, I would say cooperation is the key. And that's why we work in very broad teams. We are part of consortiums, we collaborate so we can tackle these challenges, which certainly are very demanding. And I think that's one of the keys, working at the interface of different disciplines to try to solve common problems. And yeah,
Thank you so much for sharing both your perspective and then also your research. I found it really interesting hearing specifically about how like plastic can be like recycled through chemical processes instead of just mechanical ones. Yeah,
yeah,
thank you for joining
absolutely.
today.
Thank you for your time and your questions. Very happy to chat again. Yeah.